Okay. Hello, everyone. My name is Amit Pundir. Welcome to this LMG session. In this session, we will talk about AOSP common kernels, Android 4.4 in particular. AOSP, as most of us, I believe, are aware of, that it stands for Android Open Source Project. It hosts all the open source components of Android operating system, including the kernel. And to keep it simple and short, I'll use Android and AOSP. It will just mean Android kernel, AOSP kernel. Okay, so here we go. This is the session layout. This is a quick overview of what I'm going to cover in this session. I'll start with AOSP common kernels, a brief background on out-of-tree patches and how they have evolved over time. Then we will switch to, then we'll take a look at Android 4.4 patch set, a brief introduction of the functionality of all these out-of-tree patches, their use cases in Android, and their past upstreaming efforts and their current status. Then a quick intro of linaro-android-llct tree. Linaro-android-llct is a small LMG project which we host. It is you can think of it as a latest Android LTS patch sets rebased to latest Linux release tag. So for example, linaro-android-llct today is on linaro-android 4.8, which I will tag once 4.8 is out. And then we'll do a quick comparison of Android 4.4 patch set, how it stands when you compare it with the mainline tree. Because most of the patches are either upstreamed or they have been dropped from the Android kernel. So we'll take a look there. And last, we will talk about Android kernel patches and mainline staging tree. A brief introduction on outgoing staging activities and where do we stand there. So AOSP common kernels. So AOSP common kernel trees are hosted in AOSP tree. These are the core features or patch sets which Android developers created to support Android operating system at that time. These common trees also serve as a reference tree for vendor SOC or vendor SOC trees, or as you know, those Linux kernel trees, the Nexus kernel trees. Now the most frequently asked question is why all these patches sit outside of mainline tree, and why it is not in my Linux BSP, which I get from my SOC vendor. So I have listed down few possible reasons for their exclusion from the mainline tree based on my understanding of what all these patches do, and do we need them upstream or do we not need them upstream. So I cannot see it here. Okay, so you will find out that there are few features which are tailored specifically for Android needs. For example, interactive governor and UID-based routing. I'll talk about later why these patches, for example, interactive governor, there is something called on-demand governor already in mainline tree. So why we are not using that and why we are using interactive governor instead. I'll cover all these aspects later in my slides. Then there are few features which are rejected by upstream maintainers because they did not like their implementation, or it has to be done in a particular way, and Android chose to do that their own way. For example, MTP, PTP is there. Then there are a few patch sets or features which use AOSP common kernels as a test bed for those particular features before they try to push them upstream or try to use them in their products. Then there are a few features, so there are a few features which are available in mainline tree now, but they were not available in mainline tree back then when Android created those patches or when Android created those features to support in Android operating system. And then at last, there are a few features or few patches which Android took from their partner SOC vendor trees. For example, Sdcard FS. It was sitting in Samsung tree for a while now, and they were using it as a fuse replacement. Not a replacement, a fuse alternative, I would say. And now it is in AOSP common kernel, and if you see Android N or AOSP master, I'm not sure which one was that, but there is an option to switch between either Sdcard FS or just use Fuse instead. So in most cases, as you will find out later, that in most cases, most of these patches represent a limitation which Android developers found in Linux kernel at that time. Okay. Now this is where Android common kernel tree is hosted. You will see all the supported versions hosted there. This is just for information purpose, so nothing fancy to see here. This is where all the vendor SOC trees are hosted. These are specific to Nexus device kernels, or mostly for Nexus device kernels, or if there are any SOC vendor who is actively using these common kernels. Now, this AOSP Patchset evolution. So this is a slide which I stole from one of the talk which John Stelz gave in ELC 2011. So most of us in this room might be aware of the features listed here, because people have covered all these patches, all these features over time, and been repeatedly in the last few years. So now, so this is what the Android Patchset looked like 5 years ago. But the Android Patchset is evolving over time. Now, most of these patches, as you will see, are no longer required in Android. Either they are dropped or they are pushed upstream. So I wanted to take a fresh look at, okay, so this is what it was 5 years ago. Where does it stand today? When you compare it with Android 4.4 or maybe in the mainline, maybe with the mainline tree. So that brings us to the main topic of this session, Android 4.4 patchsets and how different it is, or what is the delta which we are carrying on top of mainline Linux 4.4 version. Okay, so this is where you can see the changelog. These numbers here are not entirely accurate because Android 4.4 kernel pulls or cherry picks patches from mainline tree as well. So they tag it as upstream or backport or all these fixes. So when you do a diff, you will find, okay, these many lines are changed or added or deleted, but they are not entirely accurate. These are not the complete Android delta. And here's the breakup of Android patches in the Linux 4.4 tree. Most of the Android patches went into networking core, then energy-aware scheduling, which is recently added. USB gadget is there, ADF, Verity boot, and all these things. I'll cover most of these patches to somewhat details based on my understanding of these patches, and we will see what is their upstream history. Have we ever tried to upstream them, or why are they rejected at that time, and what are we doing now, or if we are doing anything at all. I'll start with the networking core. So now the networking is something interesting here, because what Android does is, in Android, every application starts as a separate user ID, okay? And depending on that app, depending on that app, the user can be part of one or more groups, which again may have access to networking resources or not, based on that group ID. So this is where paranoid networking comes into picture. It's just a tiny bit of code in the mainline tree, but what it does is it maps those Android IDs to, map those in-kernel Android IDs to the user space group IDs, and then put a restriction there. Okay, so this particular group do not have access to networking resources. So these, this particular application cannot get, cannot have network access. Now, this paranoid networking, as I said, it's a very tiny bit of code, but since it does this Android IDs and match it with group IDs, that particular thing is something which upstream developers think of them as Android-specific hacks. So they either wanted to implement that using Android names, network namespaces, or figure out something like that. But it turned out, in Android developers' opinion, doing that in user space is quite a bit of lifting which they have to do just to get rid of this 100 or so lines of code in the kernel space. So this particular patch may never go upstream as such, and in the current state, it may not go upstream as such, and yeah, that's about that. So recently, I read this article on LWN about network filtering for control groups. I may not have understood that in that much details, but I think that is something which we can do to do this network-based filtering based on their control groups. So maybe someone will look at that. Next is UID-based routing. Okay, so next is UID-based routing. Now, typically a phone is connected to multiple networks at a time, and a host has multiple destinations to go to. Sorry. So a host has more than one interface to send out that particular packet. So what this UID-based routing does is it allows user space to configure those routing rules based on the UID. For example, if you have as I said, UID is not but your application which is running on the Android operating system. So it has an option to, has its own routing rules, and it can choose one routing route over another based on the UID. Now, the upstream options include implementing this using IP tables or net filters, but Android developers find it too expensive to do that at that level. So that's where it failed last time. But based on their recent activity, which I saw on their Gerrit and their test repositories, they are preparing a new Patchset to support UID-based routing, which they may send for RFC sometime soon. Okay. Next up is network net filter changes, QTAG ID, quota, and ADL2. QTAG ID and quota are used for data usage tracking and limiting. Again, the data usage tracking is based on UID and not based on no other parameters. Right. So one of the replacements which Android developers suggested was why not do it using NFQs. So I'm not sure where do we stand when it comes to NFQs, or whether Android developers will actually actually try using NFQ and get rid of QTAG ID and quota modules. Because one of the best things about, or not best things, but one of the peculiar things about using these QTAG ID and quota to use a UID-based filtering is that in an Android, let's say an example, download manager service. I mean, it can download on behalf of some other application, right? So when you do a data usage accounting, you do not do the accounting for the download manager. You put that in the quota of that particular application, which is calling that download manager service. Now, Android developers find implementing that particular part using NFQs or using the in-house in-kernel implementations like XT owner or NF accounting, pretty hard to do that using that. So I think they will stick to QTAG ID and quota 2 mainly for that particular purpose. Then we have idle timer. Idle timer is a series of U events which, so what this particular patch does is it sends a series of U events whenever an interface comes back online from an idle state. It is mainly for the user space to know, okay, so this particular interface is active and let's do something based on that. Right now, what mainline kernel does is it just updates the sysfs entries. So whenever an interface comes back online, those particular sysfs entries, it will get reflected in those particular sysfs entries. Idle timer adds U events to that. One thing I forgot to cover here is that when Android developers came up with this QTAG ID, idle timer, and even this PPP, OLAC, and OPNS protocols, these particular features were not available in mainline tree. So this is what drove them to write their own modules and have their own patches. So as I was saying about PPP, it provides a legacy VPN support. It was not there in the mainline tree back when Android developers were adding support of legacy VPN support in Android. Now, as of today, we can switch to in-kernel interfaces. For example, PPTP and L2TP, completely get rid of OLAC and OPNS interfaces. Sam here has done some wonderful work on that. So he just used some GPL plugins and completely got it working just with few lines of user space changes. But the problem here is that those are GPL plugins, and it's difficult to see how those plugins as it is will go to Android AOSP or not. Energy-aware scheduling is, again, it's a new scheduler feature which is being currently under RFC or currently being discussed on mailing lists. What it does is it makes the scheduler more energy-aware instead of just being a, go for a performance-based, just to be, instead of having more performance-driven, just let's take energy into consideration as well. Most of the developers, Linaro, ARM, and from Google and other mainline developers are working on it. There are a lot of talks in this Connect regarding EAS, so I will not cover. Frankly, I don't even know most of these features, what they do. So you will find plenty of developers here, and you can just talk to them if you are interested in this topic. So all these features is what EAS developers have developed. Okay, so one interesting thing to cover here is the scheduler frequency, scheduler-aware CPU frequency management, because I'm going to cover that in case of interactive governor as well. So what it does is, instead of doing this frequency scaling from the CPU freak point of view, developers, the scheduler is now making the call. Android USB gadgets. Okay, so there are a few Android USB functions which are sitting outside of mainline tree. MTP, PTP is mostly used. So the MTP, PTP implementation of Android uses in-kernel drivers or in-kernel functions. So when people try to upstream those patches as it is, the feedback was that they don't want to have an in-kernel function. So they want to have this functionality implemented on top of function FS instead. So this is where it stands today. Audio source is something which I'm not sure how people have looked into, but at that time when Android came up with the audio source driver, USB gadget, I don't think Android USB audio class drivers were there at that time. But now that mainline supports USB audio class, yes, USB drivers, so we can maybe either merge in whatever features are specific to Android and just merge them in mainline tree. Accessory drivers or accessory devices as such are not that common, and I've not seen much activity based on these drivers or any discussion if anyone is actually trying to using them outside of maybe Google Teams. Another patch set which is part of USB gadget patches is Android device class. This is a sys class interface which they are using mainly for, right now they are using mainly because their composite driver is still using this SFS entry to make the calls, that okay, Android, that okay, what is the state of this particular UDC is, if it is connected, not connected, and everything. Once we move to config FS, Android has already moved to config FS gadgets, but this sysfs entry is something which Android developers want, not Android developers, so these mainline developers, they want this sys class entry to be picked up from the UDC code instead. So instead of having your own sys class Android USB and others, other interfaces, just use sys class UDC and maybe state for the state changes. One more feature here which I forgot to put here is the event notifications. Whenever a USB state change occurs, Android patches will just send a U event to user space that, okay, I have moved from connected, someone has pulled out the plug or someone has replugged the cable. Again, mainline developers want that U event to be sent from UDC instead, because UDC already has a U event handler for that. So all you need to do is just fire these U events from the UDC instead of firing it from config.fs. Then there are a few RNDIS fixes, data aggregation or multi-packet support. There is a very brief discussion on this Patchset online, where mainline developers want them to either do it at the networking layer or use a high-end USB backend instead. Then there are a few miscellaneous tethering fixes. Most of them were related to composite gadgets. And few of them we tried to upstream, and we were actually succeeded in pushing a couple of them upstream and dropping them from AOSP as well, which are no longer required. Atomic display framework is, again, something which Android developers came up at that time because atomic update support and explicit fencing was missing from DRM KMS driver at that time. So now that explicit fencing and this atomic mode setting support is now in DRM KMS, we are not going to use this particular framework anymore. So it is still there in 4.4, but I'm pretty sure that in next Android LTS version, it will just go away. Now, verified boot, this is a new patch set which recently got added. Most of these, I will just divide these particular patches into 3 parts: dm-verity, dm-verity FEC, and dm-android-llct. Now, this verified boot and forward error correction, FEC, these are just upstream backports. These are not part of 4.4. They were backported from the latest kernel versions. So they're already upstream, so nothing to do there. dm-android-llct is something which right now is Android specific. dm-android-llct supports that AB partitioning scheme, or as commonly known as seamless updates in Android N. I've not looked into the code specific parts of it, so I don't know if it is upstream ready or if upstream will ever going to accept this in its current form or not. Sdcard FS is again similar to your verified boot. It's a new entity in Android 4.4. Not just 4.4, they moved it to, they merged it in 3.18 as well. So this is Fuse alternative at this point, but there are plans to use it as a replacement for Fuse in the upcoming versions. As I've said earlier, that right now you can just, based on a particular property, you can switch between Fuse and Sdcard FS. The common rationale behind this is that Fuse, that the performance overhead in case of Fuse is too much when you compare it with Sdcard FS. And since Samsung is already using this in their phones for last 3 or so years, they just pulled it from there and merged it in common tree. There is no upstream submission for this particular version. This Sdcard FS is derived from something called wrap-fs. And there was just one discussion which I could find online. And that was like, okay, I want to use this, and if anyone is interested, and that's about it. So I did take a look at the code base of Sdcard FS, and similar to paranoid networking, I found those Android IDs which are specific to, Android user IDs. So my guess is that if paranoid networking patches did not go because of that, so this do not stand a chance either. So let's see, but no one at least I'm not aware of any upstream submissions for this. FIQ debugger is a low-level kernel debugger for ARM. You see all those. It uses a fast IRQ interface for debugging. Daniel Thompson from Linaro was working on it, and he is still pushing patches for this particular feature in KDB. Last time when I checked, the in-progress items were enabling this for ARM v8 in mainline tree, extended NMI watchdog support, and IPI FIQ for ARM. These are the particular drivers, key record and key reset drivers, which are an input subsystem of the kernel. Think of it as all these Android phones, you press different key combinations and you can either boot to recovery or it can perform some other action based on those combinations. So this key combo driver takes care of that. Chunks of it says it is already upstreamed in sysarq driver. Other patches in input subsystem consist of generic GPIO input-output support to support complex keyboard matrices and direct input outputs and other such things. Interactive governor is again one big chunk of code which is sitting outside of mainline tree. So the biggest bottleneck it got nacked because upstream developers wanted to have this frequency selection based on the scheduler input instead of doing it from the CPU freak. So now that Shedfrek is there, Viresh from Linaro has submitted an revised implementation of interactive governor, which is under RFC right now. We hope to see that merged in sometime soon. Now, apart from these patches, so these core patches which went into different particular subsystems, there are small fixes which are spread across all the mainline, spread across the different frameworks of mainline tree. For example, this is one useful feature called private anonymous memory. Sorry. Private anonymous memory tagging. So it allows user space to tag the memory which it allocates from different sets of heap. So in that way, it can track their usage. It can track if an application crashes somewhere because of few memory issues. It can track back the issues there. Next is there are a few C group changes, control group changes, where Android puts a hack to move a task between different C groups. Timer slack PID is again something which, actually this is something which John Stultz has worked on, and it's an alternative for this is already upstream. And right now Android uses both the implementations. This timer slack PID implementation as well as timer slack NS interface, proc interface. What it does is it changes the timer slack value of a particular thread if it has permissions to do that. Then there are a few changes in Power framework for wake-up reason logging and report wake-up source. Mainly for stats purpose or mainly for debugging purpose, that okay, if a system is spending too much time coming up out of sleep mode, then what is the reason, and it will just log it there. UID CPU time is again for stat or debugging purpose, where you track CPU usage per UID. That okay, per UID means per application. So battery service in Android uses this particular feature. Then there are a few architecture specific patches which append DTP at the end of your image or image.gz. There are a few low-level print cape support and command line extension support. I've been told that most of these features are upstream now, so we'll see if we can get rid of these AOSP patches and use those mainline patches instead. Then there are a few event tracing patches in MMC, GPIO, and low memory killer framework. Few patches in MMC, as you can see, additional retries on SD detection, embedded SDIO support, and this is one new interface which they have added recently for IO latency histogram. Next one is dual role USB PHY sysfs interface. It's again a sysfs interface to track or to change the state of a dual role USB from user space and select whatever mode you want to select. Memory state time driver is again new driver which recently got added in Android 4.4 kernel. It tracks the time spent in different frequencies and DDR frequencies and bandwidth states. I did not run into any upstream submissions for this one, but this one looked quite interesting. Then we have Android Pipe and Goldfish emulator support. Most of this is already upstream. This is that Android emulator which developers can use to write their applications and use ADB to test it. There are a couple of SE Linux hooks which are Android user space specific. For example, there's a patch which you need if you are running Android Marshmallow. And there is one TraceFS file system specific patch. This is kind of a hack because Android mainline developers want to implement it based on certain rules, and just to, just a one line of change, so they say, okay, let's do it, right? Just do it this way now, and we will tackle with the correct implementation later. And finally, Android config fragments. These config fragments recently got merged mainline. Rob Herring merged them online. Right now, these config fragments only contain the fragments which are available in mainline tree. So Android still contains about 4 or 5 patches with the config fragments which are specific to AOSP kernel. Okay, so now that we have talked about Android 4.4 patches, there are a few patches which, if you compare with 4.1, there are a few patches which were there in 4.4, 4.1, and now they are not in 4.4. Because as part of LMG, we took up this small cleanup project where we looked at Android 4.4 patches and tried to figure out whether we need this particular AOSP patch or not. If there is a mainline replacement which we can just push AOSP to use, or just drop that particular functionality altogether. So we were able to get rid of switch class and GPIO support in favor of XCON, EXTCON. UID stat and network activity stats is something which they were using prior to using QTag ID and Quota2, so we were able to drop that too. Then DCC driver, it's already upstream, so we got rid of whatever AOSP has in their tree. Then there were a few duplicate drivers or duplicate functionalities which we again managed to convince them and get rid of them. And few obsolete Android composite gadgets. As I said, there were a few tethering fixes which are specific to composite gadgets and no longer required if you are using config FS gadgets. So we were able to drop them too. Okay, so next up is linaro-android-llct tree. Just like AOSP cleanup project which we took up as part of Android upstreaming. This is again an LMG project where we rebase Android 4.4 patches or whatever is the latest Android LTS patches to the latest Linux release tag. For example, right now our linaro-android-llct tree is on 4.8 RC5. So how it helps us is, it will help us, okay, I have listed down here how it helps us. It helps us find, report, and fix Android-specific regressions in mainline. We did that in past, and we do that even now. Just like commentary, it serves as a purpose of using it as a test bed for patches, which we are trying to upstream for RFC. And this is a success story for us. It can be used as a reference implementation or experimental preview to what we think that the next Android common kernel will look like. So when we were on linaro-android 3.18 tag, and Android came up with AOSP 3.18 experimental kernel, we pushed out whatever patches we had, all the fixes, and they got accepted there. Same thing happened in case of 4.1. We sent them our tree that, okay, this is what we have, and once you plan to move to 4.1, you might want to take it as a reference, and it helped there. In case of 4.4, they just picked whatever tree we had. They did not even use their internal tree. So they just used whatever tree we had, specific to linaro-android 4.4 tree, and they pushed it as experimental Android 4.4. And we hope that we'll be able to repeat the same thing for next LTS version as well. Right, so now that I have covered what linaro-android-llct 3 stands for, so we can compare the Android patch sets with respect to 4.8. So this is what the actual number looks like. This is if you compare, I'll compare it. So the usual suspects are there, networking, gadgets. You see ADF is not there because we are pretty sure that ADF is going to be dropped in the next version. Verity boot also dropped from like 10% to 4% because FEC and verified boot is already there. So this 4% is only the AB partitioning patches. So this is what the delta looks like. I have compared it with 3.18, 4.4, and 4.8 LLCT. This green part is the EAS patches because our LLCT tree do not have these patches right now. So you can see the drop here, the lines of, but this drop again is not entirely accurate because AOSP common kernels, they pull back or cherry pick upstream patches, which are part of 4.8 but not part of 3.18, but they're already upstreamed. But the drop here is quite interesting to see and quite encouraging to see actually. Right, so I have already compared that, you cannot compare these trees because of no ASP policy of cherry picking those patches back into common kernels, and we have already dropped the ADF. We no longer carry EAS patches. We don't carry EAS patches in LCT yet. And there are a few patches which we have either dropped from AOSP or we have already pushed them upstream. For example, there are a few patches, timer slack, MMC, config fragments, and other T3 specific fixes. Okay, so now is the last section of my talk is Android patches in staging, their current status, and if there is any work going on in moving from staging to main tree. Now the first one is ashmem. It's a anonymous shared memory. It's a file descriptor based memory sharing mechanism. So yeah, so one of the cool features of this ashmem is that it can discard memory units when it comes under memory pressure. So they call it as memory unpinning. Now this memory unpinning feature is something which is currently missing from mainline tree. Now John Stelz tried to implement this memory unpinning using volatile ranges, but it turned out to be a bigger deal than compared to just support a file descriptor based memory mapping. Another reasonable replacement which John looked at is memfd. So the only thing which is, memfd is again file descriptor based memory mapping. And the only thing missing again from this framework is memory unpinning feature, which is currently in to do. Then we have low memory killer feature in staging tree, which is like more of a, you can compare it with out of memory killer feature which is there in Android, which is there in mainline tree, but it is more aggressive in nature. Out of memory killer kicks in when Android completely runs out of memory pages. Whereas low memory killer, it don't wait for that long. It just kicks in way too early. So that's what it does. Memory notifiers is what people are looking at, and whether they want this killing applications to be handled through user space. So just send the notifications or notify the user space that okay, we are running out of memory and this particular application is something you should get rid of. So mainline developers are looking at, so developers are looking at using mem pressure notifiers as LMK replacement. It is again something which is in to do right now. Last time what I've been told or what I read somewhere is that it's not matching what the in kernel low memory, it's not still comparable to what in kernel low memory killer is up to. So yeah, so this one is in to do as well. Sync and software sync, Gustavo is working on that. Most of this is already destaged and moved to DMA buff. Software sync is moved as a debug FS interface. Sync APIs are used to synchronize buffer transfer in between complicated pipelines. So this is something which is actively being worked on and hopefully get destaged from staging. Ion is again a memory manager which was Android specific, mostly used in graphics pipelines, but can be used as a generic purpose memory allocator as well. Laura from Red Hat was working on it, is working on it. Current in progress items are device tree bindings and better discovery of available heap IDs to allocate from a new ioctl interface to support caching using DMA buff APIs. So this is in active development right now. So this is what I showed you earlier. That okay, so 5 years back we had this snapshot of AOSP patches sitting outside of tree, and you can see that all the green ones strikeouts are either already in staging tree or they're merged. They are already merged in the main tree. Red ones are completely dropped out. So, but while a lot of effort has been gone into, just shrinking that delta, a lot of new features have been added as well, like as we have seen that in my talk. And there always will be something new or innovative which Android developers will come up with, and they push it in their AOSP tree. So that's all I had. If you guys have any questions. Right, we have one there. Yes, so the closest to interactive governor was on-demand governor. Now the peculiar thing about interactive governor was, as soon as you wake up from sleep, it will just shoot up your operating frequency to the maximum level. And only on-demand governors don't do that. I think that's what the reason, right? I mean, I'm not an expert on that, but that's what I've figured out from the discussions which we have. All right then. Thank you very much, guys, for coming.